introduction. Many thanks to the organizers for this invitation. So I'd like to start with to the audience, which is what is the most important duty of the final speaker? You want to know?
Organizer.
Yeah,
Is that more important than giving the final talk?
Yeah, and normally this happens after the talk, but I easily get muddled and forget things, so I want to get it out of the way at the beginning. So when Alex started organizing this conference, I thought it's a really brave thing to attempt to organize a conference that is a worthy celebration of Hendrik's many astounding mathematical achievements. And then when I heard that John joined, I thought that makes a lot of sense because John is the bravest person I know. But it's been a beautiful week, riveting mathematics and hugely entertaining talks. So thank you both very much. Please join me. Okay, so I thought final talk last day, everyone is tired, so it'll not be very serious. I'll just it'll be a heartwarming talk, you know, of a tale of personal growth and self-discovery. It starts in 2018. And so 2018, working with Freitas and Klaus, I proved this theorem. And I talked about it at Simon's collaboration conference at MIT. And the theorem is about the asymptotic Fermat's last theorem over this family of number fields. So UN2 is the nth layer of the Z2 cyclotomic extension of Q. You saw that, you saw such things in René's talk. So here are the first few, the Q, Q2, and so on. And asymptotic Fermat's last theorem, what that says is that there's a constant that depends on K, such that for prime exponents greater than that constant, the Fermat equation with that exponent only has trivial solutions. Okay, now you might be looking at this and thinking, Samir has already started his talk, and he forgot to say anything about Hendrik and his acts of his great deeds of valor and heroism in the pursuit of mathematical happiness. But that's still to follow, because Hendrik was at this talk, and one thing I'm sure that you've all noticed is Hendrik's amazing mental presence. That quite often I'll in my talks when Hendrik is there, it's obvious from the discussion during the talk and after the talk that Hendrik has understood my talk better than I did. Okay, so during that talk, about 2/3 of the way, Hendrik points out that the proof I just explained works for a much bigger family of number fields. It works for any two extension of Q unramified away from 2 and infinity. So for example, it works for this, which doesn't fit into that family. And that evening, I actually didn't understand. I didn't understand why the proof works, but for this bigger family of number fields. But that evening, I was having dinner with Hendrik and Alex, and I asked Hendrik about this while we were waiting for our food, and he took out his writing pad and very kindly wrote 2 pages which explain the theory of P groups and P extensions, and full details of a paper of Iwasawa that he read 30 years earlier, but perfectly recalled the arguments. And I took that away and studied it for 2 weeks. And then I realized, yeah, okay, Hendrik was right. Okay.
So
So
this is still for finite extensions.
yeah, this is fine. Yeah, finite. Two. So it's not a Pro2 extent. It's okay. So yeah. So but then I said to my collaborators, obviously we've missed a lot of stuff. We really have to look again and think about Fermat, not just about the Z2 extension of Q, but general L extensions, and we managed to prove this theorem. Okay, so the theorem says that if L is a prime, so an L extension, K is an L extension. L extension means it's a number field, it's a Galois extension whose degree is a power of L. And we impose some conditions. K is a totally real field. L is totally ramified in K. 2 is inert in K. Then the asymptotic Fermat's last theorem holds for K.
Isn't the first condition automatic? It is of degree, so there is no.
Yeah, of degree. Yes, you're right. Yeah, you're right. Yes. Okay. Okay. So, and you will. So the hypotheses are satisfied for the nth layer. If you take the nth layer of the ZL cyclotomic extension of Q, where L is at least 5, provided that the L is a non-Wieferich prime. Okay, so non-Wieferich means this. Okay, and you need this condition because this is a condition for 2 to be inert in this extension. Yes.
Just to clarify, it looks like you're not forbidding ramification away from L. I mean, you're forbidding it at 2.
Exactly. Yeah.
Because, I mean, this example is only ramified above L, but the theorem does not require this.
Yeah, but you want anything can happen at other prime. Exactly. Yeah.
If 2 is inert, the extension must surely be cyclic.
Oh, so you're saying that it only applies to this?
Well, the decomposition
No.
group at 2 is cyclic, right?
Yeah. Yes.
Well, no,
That could be
because
other-
there may be other primes ramifying.
Yeah. This is the point. That this doesn't. I mean, we're not saying anything about any other primes. Anything can happen at any other prime, but I need this behavior at L and at 2. Okay. So maybe I could say one lesson from Bjorn's talk is if you have a Diophantine problem and you can't reduce it to the unit equation, then you're probably not going to be able to solve it. And this is true here, although the reduction is very different. But a key step is showing that the unit equation for such field has no solutions. Okay, so so this talk is not really about Fermat, it's about unit equations, but Fermat was the sort of the way in for me. So that's why we talked about it. Okay, so here's so we want to show that the unit equation for such field doesn't have solutions, and we'll start off with a lemma, and the lemma is you take an L extension, so it's a Galois number field of degree L to the n, and we assume that L is a totally ramified prime. So the ideal generated by L is lambda to the degree where lambda is a prime ideal. And then the lemma says that any unit in this extension has to be plus or minus 1 mod lambda. Okay, let's look at the proof. It's not a deep result. So let G be the Galois. Now the first thing you need is that because the prime is totally ramified, Galois group is the same as the inertia group. Okay, so I take a unit, or this is the slide, any integer in the number field, then well, you don't see the action of inertia modulo the prime. Okay, so epsilon, that's the definition of inertia. Epsilon to the sigma is going to be congruent to epsilon mod lambda for all elements in the inertia group, but that's the same as the Galois group. Okay, and then if you take a unit, well, its norm is going to be plus or minus 1. The norm is the product of the conjugates, but if I'm working mod lambda, each conjugate is congruent to epsilon, so I get epsilon to the L to the n, and because my residue field is FL, again, the prime is totally ramified, Fermat's little theorem tells me that this is the same as epsilon. So I've proved the lemma. So there's nothing deep or clever here. And now I have the same hypotheses. I've upgraded the lemma to a theorem, the same hypothesis, but I've added the condition that L is not 3, and I've changed the conclusion to the unit equation has no solutions. And the proof is, well, this is plus or minus 1, this is plus or minus 1, plus or minus 1, plus or minus 1 is not 1 mod L. Mod lambda is the same as mod L. It's not 1 mod L unless L is 3. Okay, so and that's all. Okay, proof is finished. Unit equation doesn't have any solution in this big family of number fields. Okay, so we can prove asymptotic Fermat's last theorem for lots of L extensions when L is not 3, but we just, you know, the proof doesn't work for L equals 3, so we were unable to prove. Okay, for this, and then you can ask, does the unit equation have finitely or infinitely many solutions here? I mean, if it has finitely many solutions, there's still hope. Okay, to do the asymptotic Fermat's last theorem, if you can pin down what they are. Okay, so let's move on and maybe look at things in a much broader. So I'm really interested in Siegel's theorem, but not for number fields. So here K is a number field, but Siegel's theorem, when you're talking about U in replacing the number field by U infinity. but somehow, I mean, I owe this point of view to many books and papers by Lang. Somehow you shouldn't look at these great theorems separately. You should just study them together. Somehow they're all interrelated. So what are they? Well, I think you know most of them. So there's the Mordell-Weil theorem. If you have an abelian variety, the Mordell-Weil group is finitely generated. Let's skip the Tate conjecture for a minute, and the Shafarevich Mordell conjecture or Falting's theorem. You all know it. Like the K points on a curve of genus to that set is finite. And Siegel's theorem was mentioned in Bjorn's talk. If you have a set of a finite set of prime ideals of OK, then the unit, the S unit in this equation has finitely many solutions in S units. Okay, the ones I skipped over are the Tate conjecture. Possibly this one is the least familiar. But I guess the sort of the way I like to think about it, you have two abelian varieties and their Tate modules give you isomorphic Galois representations, then they have to be isogynous. And the Shafarevich conjecture says that if you fix a finite set of prime ideals, n is at least one, it's going to be the dimension, then there are finitely many isomorphism classes of dimension n principally polarized abelian varieties with good reduction outside the set S. Okay, so these middle three, Tate conjecture, Shafarevich conjecture, Mordell conjecture, were all proved by Faltings in the same paper. Siegel's theorem, that's in 1920s. So here are, I mean, this is not exhaustive by any means, but there are some relationships. So when Faltings proved the Tate conjecture, from that he deduced the Shafarevich conjecture, and then from that used the Mordell conjecture. And nowadays, people think, modern people, not me, think that Faltings theorem and Siegel's theorem are one statement. You know, they call it Faltings-Siegel. So you saw something like this in Bjorn's talk. You have a number field, K, a finite set of primes, X is a hyperbolic curve over this. Then the S integral, the set of S integral points is finite. And here I think, you know, we should have some kind of curvy. We should choose a model, but that's not important for this talk. So an example of a hyperbolic curve is E1 minus 3 points. And just in case you've missed it, let's just see why. Let's just try to understand why the integral points of this are the same as the solutions to the unit equation. So the meaning of an integral point on P1 minus 0, 1, infinity is, well, it's going to be an element of K, your P1, that doesn't reduce to 0 or to 1 or to infinity modulo any prime ideal. Okay, and if something doesn't reduce to 0 or to infinity, it has to be a unit. And because it doesn't reduce to 1, then 1 minus epsilon has to be a unit. So epsilon 1 minus epsilon are both units. You get a solution to the unit equation. Okay, Now let's look at the same table, but over Q infinity. What is known? What is conjecture? And the first step is that. If you look at the analog, the Mordell-Weil theorem, that is a famous conjecture of Maser from the 70s. So it's a famous conjecture in Iwasawa theory. The analog of the Tate conjecture is a theorem of Zahin from the early 90s. Let's skip Shafarevich for a minute. Analog of Mordell is known as the Partian conjecture. Okay, so same statement as the Mordell conjecture. So this is a conjecture from the 70s, and it doesn't seem that there is anything in the literature about Shafarevich
Or some
or
prime
Siegel.
I assume it's the VP extension.
I should point out that
It's still an index L.
when I say Partian, this is not the famous Partian conjecture, but a Partian, a conjecture of Partian.
Can you remind me what Q infinity is?
Yeah, it's Q. Well, it's the ZL. You fix a prime L, and you look at the ZL extension of Q. So
Any L.
any L, yeah, any L. Okay.
So L equals 3 is included here.
Yeah.
But then the answer is no.
Yeah, exactly. The answer is no. Yeah, but it's all right. But you have to. I mean, you have to ask yourself: am I asking precisely the right question, or is there a variant of the question where the answer is yes? So so we shouldn't sort of fix a statement. And okay, right. Yeah. So I told you about Henrik at the beginning of the talk. So he knows what is coming. He knows what is coming next. But before we go into that, the rest of the talk is about Siegel and Shafarevich and why there doesn't seem to be a sensible finiteness statement that you can make when you're working with Q infinity. There is a survey article by Zahin and Partian from the early 90s, which they mention the Partian conjecture, and the evidence for it is that Zahin proved the Tate conjecture, and so that seems to be saying, look, faultings through Tate and then deduce Shafarevich and then deduce Mordell. So maybe there's a path for to go from the analog of Tate through some version of Shafarevich to the Partian conjecture. So this talk, it's about that doesn't seem to be such a path. Another thing that I'd like to say is to make an apology, because about 2 years ago I spoke in a number theory web seminar. So maybe half the world's number theorists were there, and I made a mistake, and I said, you see, if you believe in the Partian conjecture, then you should believe that the analog of the Siegel conjecture, just like there's faulting Siegel for number fields, there should be Partian Siegel or Q infinity And in my so that's wrong. Okay, that's a point of the talk. And but in my defense, I was misled by a true expert who, because this talk is being recorded, will remain nameless. Okay, so so as Hendrik has predicted, so here's okay. So we had an example. We had a question. So Q infinity L, where L is not 3, we know that the unit equation has no solution. I'll prove that at the beginning. But Q infinity 3, like L equals 3, then you have infinitely many solutions, and the solutions appear at every level, every layer. You get new solutions that you haven't seen at the previous layers of the ZL extension. And if you take L to be 2, 5, or 7, then well, okay, we know that the unit equation doesn't have solutions, but let's look at the S unit equation. Well, S is the unique prime above L, so L is totally ramified here. Then this set is infinite, or you could say that this equation is infinite, where epsilon and delta are S integers of this equation. And again, you see solutions appearing at every level. Okay, so to sort of understand this, maybe we need to revise a little bit about cyclotomic units. So you've seen these in René's talk. But so one thing so I'm going to take zeta to be an L to the n+1th root of unity, and one thing you probably know is if you take this and you plug it into x to the m-1, and L doesn't divide m, then you get the unique prime ideal above L. Okay, so you get an S unit. Well, S is the primes is the unique prime above L, and so that tells you that these things here, when I take data and plug it into here, I get an S unit, and you can go between, back. So you could, so probably this factorization is familiar if you've seen cyclotomic polynomials before. You can go from this to this using the Mobius inversion formula. So mu is the Mobius function, and this helps you if you've seen cyclotomic, the version of cyclotomic units in René's talk. It helps you to translate to this. Okay, so the cyclotomic units in here, you can take this as a definition, but this has the advantage that if you mod out by your zeta, by a subgroup generated by zeta, then what is left? A free basis. It's a free basis for psych n modulo zeta. And sometimes we'll work with what I call cyclotomic S units, where S is the unique prime above L in this field. And so all you have to do is take this and allow m to equal 1, because when m equals 1, phi m is x minus 1. So you're just looking at zeta minus 1. That's a prime ideal. Okay, and you can sort of talk about cyclotomic units inside inside here, and a cyclotomic S unit. So this is the real subfield of the cyclotomic field. And you've seen in Mané's talk the Kumar-Sino theorem, which tells you that the index of the cyclotomic units in the full group of units is class number of this field. Okay, but that's also true if you take the cyclotomic S units inside the full group of S units. You also the indexes. So this result will not need till later. Okay, now let's do an example. Okay, and this example, well, it's not about epsilon plus delta equals 1. It's about epsilon plus delta equals 2. But what I wanted is just one example which fits on a slide and has all of the ideas in it. Okay? And if you like this kind of stuff, maybe you can find your own examples. We have a bunch of identities that generate examples in the paper, but we don't claim at all that they are exhaustive. Okay, so I'm going to take L equals 5. Zeta is the 5 to the nth plus 1 root of unity. I mean, I'm taking this because the nth layer of the Z5 cyclotonic extension, it lives inside Q zeta, and the Galois group is cyclic of order 4, and it's generated by this automorphism. So you know every automorphism of Q zeta is of the form zeta goes to zeta to the A, where A is invertible mod L. But if you know, because this is cyclic of order 4, you want to choose A to have multiplicative order 4 modulo 5 to the n plus 1. So, you know, A squared is minus 1 modulo 5 to the n plus 1. Okay, now we have 3 polynomials, and they have some properties. One of them is f plus g equals 2h. Another one, they're not symmetric polynomials. They're not S5 invariant, but they're invariant under the cyclic permutation of the variables. Okay, and the third property is that they are really products of homogenizations of cyclotomic polynomials. Now, if I take a bunch of powers, you know, not necessarily these, but powers of zeta, and I plug them into F, well, you know, here I'm going to have a root of unity, here I'm going to have a root of unity, here phi3 evaluated at a root of unity, which ought to be a unit, unless the ratio is 1, and phi3 evaluated at another root of unity, that ought to be a unit. Okay, so F evaluated at random powers of zeta, that's a unit. But now, if I evaluate at these powers, you know, zeta to the A, zeta to the A squared, zeta to the A cubed, yes, I mean, that's a unit, but not not just in Q zeta. It's in Q and 5. It's a unit of Q and 5. Why is that? Because when I act on this by the generator of the Galois group, I just permute these values cyclically, and F is invariant under cyclic permutations of the variables. So I end up with a unit in here, and same for G, same for H. So then, yeah, I get, well, I get unit plus unit equals 2 times unit. So dividing by the third unit, I get solution to epsilon plus delta equals 2 in units. But you see, I mean, as I vary my zeta, as I vary my n, okay, I get new solutions in every layer. And so I conclude that there's infinitely many solutions, or another way of saying that is this is infinite. So Siegel's theorem, I don't see a way of, I don't see a way of rescuing it, but maybe someone could come up with a proof that there's, a complete classification of such identities, such identities, and maybe this might, then maybe there's a conjecture that apart from several infinite families of solutions, that you should have finiteness. I don't know. Okay, so that's an open problem. Let's move to the Shafarevich theorem, or the Shafarevich conjecture. And there's sort of many ways that Shafarevich can go wrong, but here is one of them. Take a random elliptic curve. So this elliptic curve here over rationals has conductor 32, so good reduction away from 2. L could be anything. You take a unit you take a unit in the unit group of Q infinity, and you look at this quadratic twist of that elliptic curve. It's going to have good reduction away from the primes above 2. Okay, I should have said this at the beginning, that if you fix a prime, then a rational prime, there's only finitely many primes in Q infinity above that prime. There might be some splitting as factors, you're going up the layers, but it stabilizes eventually. Okay, so now you see this has good reduction away from the prime above 2. And if you take 2 twists and ask when are they isomorphic, they're isomorphic if and only if the ratio of the units is a square. And so this group classifies twists and units modulo squares. In a number field, this is finite, but here this is infinite. And so you obtain infinitely many isomorphism classes over Q infinity with good reduction away from 2. But one thing, one sort of drawback about this is that these things, they give you infinitely many isomorphism classes, good reduction away from 2, but over Q bar, they're all isomorphic to E. So over Q bar, you only get one isomorphism class. Okay, so maybe, you could sort of wonder, is there a version of Shafarevich that works over Q infinity? And we sort of struggled a lot with this, and we came up to counter examples to lots of conceivable generalization. But here's one of them. So this works for any prime L, but the genus, okay. So the dimension of your abelian variety is going to depend on L. So I take L to be at least 11. There's constructions for smaller primes. Is to keep things simple. L is at least 11. There's a need odd. Is a prime, and G is going to be the floor of L minus 3 over 4. Then there's an infinite family of genus G hyperelliptic curves over Q infinity with good reduction away from the primes above 2 and L. This is a finite set. again, these appear over every layer, and the curves are pairwise, non-isomorphic over Q bar. And the Jacobian, Jacobians are going to have, well, okay, trivial from known facts. The Jacobians are going to have good reduction away from this set, and by Torelli's theorem, they're going to be pairwise non-isomorphic over Q bar. Now here's the thing: we thought maybe you know, well, all of these things they come into finitely many isogeny classes. Maybe that should be the statement. Okay, so for some small collection of primes, the Jacobians are in fact pairwise non-isogynous over Q infinity. Okay? I mean, I don't know. I mean, the other primes, I presume, the same is true, but I don't know how to prove it. So maybe people can offer suggestions afterwards. Okay, but here's how the idea works. Okay, so again, zeta is going to be the L to the n plus 1 root of unity. I'm going to take two powers of zeta, so an alpha and a beta, and I have an identity. It's got nothing to do with the fact that alpha and beta are roots of unity. It's just an algebraic identity. Alpha plus alpha inverse minus beta plus beta inverse. I can write it like this. Okay, but now because these are roots of unity, 1 minus a root of unity is a cyclotomic S unit, and 1 minus another root of unity is a cyclotomic, unless you have this in which you get 0. Okay, so now I'm going to take gamma 1 to be this zeta plus zeta inverse, and this Galois group has so zeta plus zeta inverse is in Q zeta plus. This Galois group has degree L, this has order L minus 1 over 2. So I'm going to take a full set of conjugates of gamma 1, and I'm going to look at this hyperelliptic y squared is x minus gamma 1, x minus gamma 2, and so on. So it looks like this is defined over the cyclotomic field generated by zeta, and that's true. But this polynomial on the right-hand side, you notice that when you act on this by this Galois group, you're just cyclically polluting the roots. So in fact, the coefficients of the polynomial live in the nth layer of the ZL cyclotomic extension. Okay, so this is a curve defined over the nth layer of the ZL cyclotomic extension. And if I look at the discriminant of the hyperelliptic polynomial, well, I'm multiplying differences of these expressions, gamma I minus gamma J, which are root of unity plus its inverse minus root of unity plus its inverse. And these things are cyclotomic S units. Okay, so the curve is going to have good reduction away from the primes above Q and L, and it has genus this. We've constructed the curve, and you can check that they're by just looking at the invariance of the curves, that they're actually pairwise non-isomorphic over Q bar. But now let's look at why they're non-isogynous for some values of L. Okay. And I apologize that your slide has lots of stuff on it, but yeah, it's just a couple of tough slides, then we'll go back. Then we'll finish the talk. So the list of primes that you saw, the finite list of primes, they all have some nice, so L has the form 2 to the q plus 1, where q is an odd prime, and the and 2 is a primitive root modulo q. Okay, so let's restrict to these primes, to primes of this form. I'll explain why in a minute. I'll also need this notation. So omega infinity plus is, if you take the union of these L power real cyclotomic fields, and this is a cyclic extension of Q infinity of order L minus 1 over 2, and L minus 1 over 2 is the same as Q. And then we take the curve that we constructed at the nth layer. So this is it. I've labeled the roots as gammas, and the curve that we constructed for the nth layer, and this is it, and I've labeled roots as deltas. And now I'm going to Jn is going to be the Jacobian of Cn, and Jm is the Jacobian of Cm. So I've written a statement that is not at all obvious, which is that the two torsion on the Jacobian is irreducible as a Galois module, the GQ infinity module. Okay, and so we know that this acts cyclically on these roots, and the two torsion, the Galois action on the two torsion can be described in terms of the Galois action on these roots. And it turns out, okay, it's not hard to check, that this Galois module is irreducible if and only if L minus 1 over 2 is prime, okay, and 2 is a primitive root of FQ. So that's why I need those conditions. So where am I going to use this fact that this is irreducible? I imagine that I have an isogeny between the Jacobians at different layers defined over Q infinity, and I can suppose that it has minimal degree, and I want a contradiction. I want to show these Jacobians are never isogynous. Okay, now I've said that because this is irreducible, phi has to have odd degree. Why is that? Because the kernel of phi is well, it's a Galois module, and you can take its intersection with this. So you get a submodule of J2, and because this is irreducible, it's either the trivial submodule, and that tells you that phi has odd degree, or it's the whole thing. But then phi factors through multiplication by 2, it's not of minimal degree. Now, we know phi has odd degree, and the great thing about isogenies of odd degrees is that they preserve the fields of 2 to the r torsion. Okay, so I know that's Q infinity, Jn to the r, and Q infinity, Jn to the r are the same for all values of r. And I say, I know what to do. I'm going to compute Q infinity of the two torsion for this one, Q infinity of the two torsion for this one. And if these two fields are different, I have a contradiction, I'm happy. Okay, but if you know a little bit about this, you'll know, okay, the field, so the field of two torsion is the field that you get by adjoining the roots, but you're in a cyclic extension, you can join one of them. And this has degree, this field has degree L minus 1 over 2 or Q over Q infinity, and it's the same as this. So in both cases, you get the same field because you've adjoined the root of unity plus its inverse, and you don't see a contradiction. And then you're upset for a few days. And then you say, why don't I compute the fields of four torsion? And if they are different, then I have a contradiction. And when you compute the field of four torsion, you find that there are these polyquadratic. Okay, so the field of four torsion is the field of two torsion, which we've already computed, it's Q infinity plus, adjoining the square roots of the differences of the roots of the hyperelliptic polynomial. Okay, so if we have an isogeny, the fields of the four torsion are the same, then we get an equality of polyquadratic extensions. Okay, and when you have a field and you're taking, square root, okay, and you have a polyquadratic extension, you can say, how can I adjoin a bunch of square roots to a field and adjoin another bunch of square roots to a field, and I get the same extension? And the answer is that the groups generated by the things that you're adjoining have to, these two groups have to be the same modulo squares. Okay, so we get this, and then so just ignore this one. This is okay. Yeah, so we reached here. We have a relation here in this group Q infinity modulo squares, and now okay, so it's just to make things a little bit more concrete. Let me take delta 1 minus delta 2. It's in this group, and because these two groups agree, delta 1 minus delta 2, I can write it as a product of the subset of gamma I minus gamma j times S squared. And a priori, this mu lives in Q infinity plus, but then Galois theory tells you that it's actually in the mth layer, so this field, and then because everything is an S unit, okay, it has to be an S unit. So we have relations between cyclotomic S units, but the problem is they're up to a square of something that is not a cyclotomic S unit, it's an S unit. Well, not necessarily as cyclotomic S unit. But now we remember that this index here is the class number, okay, HM plus. And so if the index is odd, then I can deduce that mu is in here, okay, because its square is in here. And I obtain a contradiction. This is not obvious, but I obtain a contradiction because I understand, I understand this group in terms of generators and relations, and I have some relations that are okay. I can check the not. All right. So the question is, so the outcome is that if I have primes that satisfy prime L that satisfies this condition, and 2 does not divide the class number of this cyclotomic field for all n, because I have Jacobians at all levels, and I want to check that no pair is isomorphic for all M, then I obtain a contradiction. So that's what I want. And now, yeah, well, remember that okay, so this was also in Daniel's talk that the this class number of the real cyclotomic field divides HM. So HM is the class number without the plus. And here's a beautiful theorem due to Estes and to Stefan Hagen. Peter's not here, I wanted to thank him. Anyway, so under these assumptions that you've seen before, the class number of the base layer, so U zeta L, that's odd. Okay? And then you might say, okay, it's a tall order to expect that, you know, we can impute the parity of the class number for the whole, for the whole tower. But there's this amazing theorem of Washington. This is different than the theorem you saw in René's talk. That was L equals P. This is L different than P. So if you take the valuations, you fix a prime P, for example, when you take these valuations of the class numbers of the layers, then this is bounded as M goes to infinity. And this, in fact, is in theory effective, okay? But the computations they explode very quickly. So here's a theorem by Shimura and Nakajima, which says that for L less than 509, so this is how far they've got. Well, the parity of the mth layer is the same as the parity of the base layer for all m. Okay, so if you put everything together, then you get this list of primes. So for this list of primes, the Jacobians we know are pairwise non-isogynous over U infinity. Okay, so yeah, and I think I've timed things really well. So it remains to, well, let me just first thank Hendrik for being Hendrik. And yeah, maybe at the next conference we overlap, maybe I can invite you to dinner again, and you can give me a hint as to what I should do for the next 5 years. And thank you all for your attention.